Well, hello again, YouTubers. Thanks again for tuning in. Today I'm going to be talking about constant current sources and particularly exploring the LM317 and the LM7805 as precision constant current sources. So, first of all, what is a current source? Well, a current source provides a set and stable current, and it should be independent of load or voltage. So a current source will always deliver a specific current, um, preferably independent of the environment that it's used in. So there are many types or implementations of current sources. Some that are passive that use resistors and Zener diodes, others that are active like linear regulators, some that have feedback, and some without. So some of the components commonly used in current sources, you'll find op amps, Zener diodes, P-channel MOSFETs, BJTs, LM317, LM385, and you also get many purpose-built constant current source ICs, for example the REF200 or the LT3092. So since we're going to be talking about the LM317, it's a fairly old school, it's robust device. It's got overcurrent protection. It's got all sorts of safety features built in. So it's really a nice and easy to use current source as maybe your first implementation. So I recommend you try it out, and it's really easy to implement. So I'm going to be talking about that right now. So in order to use the LM317 as a current source, there is a basic output formula to use it as a current source, where current out, or I out, equals Vref over R I sat. And if you refer to the diagram below, you'll see that I out is determined by RI set, and Vref refers to the internal reference voltage of the LM317, which is usually set at 1.25 volts. So LM317 uses a Vref of 1.25, so that's a constant, and then you would be able to change the output resistor in order to determine your output current using that formula. So because the way the LM317 works, the Vref of 1.25 volts will always try to be maintained between V out and the adjust pin. So using this principle, we can ensure that there's always a constant voltage being maintained across a fixed resistor, and this gives us a constant current. So that's obviously using Ohm's law, I equals V over R, and that's how we determine the current. So below I've got a few examples of how I calculated the output current. So if we take Vref 1.25 divided by a 125 ohm resistor, that would give us an exact current of 0.01 amps, which is basically 10 milliamps. If we use a 250 ohm resistor, then we would get exactly 5 milliamps. And actually made a mistake in the bottom one. It's if we use a 500 ohm resistor, we will get 0.02 so it's 2.5 milliamps. Now, using a precision resistor for these resistor values is key in getting an accurate output. So it's always good to look at precision resistors of using an accuracy of about 0.1%, which I'll explain in the next slide. So I implemented this on my breadboard, the LM317 using a 250 ohm resistor, which has a tolerance of 0.1% as a 5 milliamp current source. And so I measured the output on my multimeter. It's a UT61B, and it showed exactly 5 milliamps. And that was without any sort of adjustment or calibration. And it was, as you can see in the breadboard, that's how I measured it. And that's using a Vishay precision resistor. So if we look at the measured results for the LM317 as a current source, I used 3 different resistor values, all from Vishay. It's the PTF56, and I measured the results each time using different resistor values. So for a 10 milliamp current source, I measured 9.96 milliamp, which is a basically a plus minus 0.4% error. And then for the 250 ohm resistor, I got exactly 5 milliamps, which indicated that there was absolutely no error in the circuit. And then I used a 500 ohm precision resistor, and that gave me 2.53 milliamps, which indicated a 1.2% error. Now, I made some notes here about the circuit to try to explain these error results. And one of the error sources that I could attribute the error to was the multimeter that I used. It's a Unity UT61B, which has a DC current accuracy of 1.2% plus 3 counts in the range of 40 milliamps. So that was the range being used, and according to the spec sheet of the multimeter, it actually can attribute the error that was seen in the measurements. However, I can't be exactly sure where the error source came from, if it was the resistor being out of spec, or the way the current the way the circuit was set up on a breadboard, but essentially it was within the error of the multimeter. So I can assume fairly safely that the error source originated from my multimeter, and maybe a smaller error from within the circuit itself. So if I had a more accurate measurement device, then I might do this experiment again and try to see how much error there was in the reading. But that's for another video. So yeah, that was pretty successful. We got quite high precision, especially with the 250 ohm that showed no error. And yeah, so I'm going to show you next a different implementation of a current source. This is using the LM7805, which is a 5-volt fixed voltage linear regulator. And this one is slightly more complicated because there is one other difference to the formula as opposed to the LM317. And the difference we need to take into account is that there is a bias current that contributes to the calculation. So this bias current is seen between the ground pin of the LM3 of the LM7805 and the output. So this was quite hard to measure because you could try to measure it with the multimeter, but because it's a very low value, it's hard to exactly find a resistive value that will give you, say, a very round number, such as 5 milliamps or 10 milliamps, which I'll explain to you next in my calculation. So what's interesting is that V out of the LM7805 is usually close to 5 volts. However, it does vary slightly according to load and input voltage. Also, the bias current, which is I output bias current, which is this, also varies according to the input voltage. So it is input voltage dependent, although very slightly. And I measure the bias current at 2.8 milliamps. So plugging this into the formula, V out I measured at 4.98, and including the bias current and the desired output current, we can calculate what value our I set needs to be, which is that output resistor. So I plugged it into the formula over here, which was originally that one, and I got an RI set value of 691.66 ohms. Now you're never going to find a resistor at that value, so you're also never going to find a LM7805 that has exactly 5 volts. So this is something you'd have to measure on a individual chip by chip basis. But essentially, because the variance is quite high, I mean, you'll have variance in the input voltage, which will affect the bias current. You'll have variance in the actual output voltage of the regulator, and you'll have variance in the temperature, and therefore the temperature drift of the resistor will also cause the calculation to vary slightly. So what I found out is that this is not a very stable or accurate way to create a current source, although it is a way, and if you have the parts, it can be useful for lower precision applications. So what I did, I implemented RI set using a 10-turn trimmer, a 500 ohm 10-turn trimmer, and a 270 ohm fixed resistor, which I implemented over there. And using the 10-turn trimmer, I could quite accurately measure, first of all, measure the output current, and then just adjust the trimmer until I get the desired current. So this is a more complex and less stable setup, and it does vary slightly due to load and input voltage. So in this slide, I'm showing you how I implemented it on the breadboard. It's quite hard to see the actual connections, but the schematic in the previous slide should give you exactly that on a breadboard. So I set the trimmer to give me exactly 10 milliamps, and that's what I measured. And to confirm the reading on my multimeter, I plugged in the measured values of the resistor that I created, and I found that using the values, like measuring the resistor, measuring the bias current, and all those factors, it actually led me to a result of an output of 9.75 milliamps. So well, this is not the best way to calculate it in reverse, because I know the reading here is probably off by 1% or so, and the other measurements I made, like the bias current, the output voltage, and the resistance value, are also affected by the multimeter's accuracy. So with all those inaccuracies added up, you you tend to get quite a high error in the calculations. So I would say that the calculation is intrinsically error prone because of so many error sources within the calculation as well. So don't look at the reverse calculation too much, but basically I just plugged it in to try and confirm to see how off my measurements were with in comparison to the actual measurement. Yeah, so below you can see the accuracy values of 1%, 1.2%, and 0.8% all added up. You probably get like just about 3% error. So when added together, you can account for the error calculated based versus the measured value. You can see the error. If you add up the error parts here, you'd get about 3% plus 15 counts. So if you look at 2.5% error, then yeah, you can attribute the multimeter to being the source of error. So yeah, I hope you learned something, and I showed you a few current source circuits that you may or may not have heard about and how to implement them. And just in conclusion, just wanted to mention it may seem logical to use trimmers everywhere because you can get an accurate reading. However, you always need to consider the fact that the reading you're getting is only as accurate as the tool, the multimeter you use that measures that reading. Additional to that, you will also find that trimmers are not very temperature stable and they can drift over time. And yeah, so the two techniques explained are cheap and easy ways to implement constant current sources. There are many other types of current sources that you can go and look up and research if you go to the Wikipedia link, wikipedia.org/wiki/current_source. They have quite a few different circuits that describe various current sources. So yeah, thanks again for watching. Cheerio.